Yes, sir.
In yesterday's class, we had seen the equations, we had derived the equations for the speed torque characteristics of an induction motor, and we had also drawn the speed torque characteristics. Correct?
Yes, sir.
Today's class will be an extension of that, and today we will see the speed torque characteristics of induction motor under motoring as well as braking conditions. Class will be a little slower perhaps because I will draw the characteristics. Okay. So we take two axes. Yesterday, I think we had taken torque on the y-axis. Is that correct?
Yes, sir.
Because
Yes,
we
sir.
wanted to see the speed torque characteristics for motoring as well as generating.
Generator.
And for that purpose, it is better to take torque on the y-axis. Today our purpose is to draw the speed torque characteristics in all the four quadrants. And so that is why today we are going to take speed on the y-axis. This here will be your speed omega. I'm writing W, but it is omega. And on the x-axis we take the motor torque. So if we do this, let us say this is our synchronous speed. Okay, here the speed is 0. The speed is now increasing in this direction. The slip is increasing in the opposite direction. So here the speed is 0, the slip is 1, and here the speed is the synchronous speed, and the value of slip is 0. Okay. So now if we draw the speed torque characteristic, we take this line as the maximum torque line. This is your maximum torque or breakdown torque, Emax. This will be the approximately, you can say it is like this. Okay. This is the, let us say, the speed torque characteristics of the induction motor without any external resistance. This is your synchronous speed. This is the preferred operating region that is mostly linear, close to the synchronous speed. This is your maximum torque. This is your SCR, slip critical slip at which maximum torque occurs. And this torque, the speed is zero. This will be your starting torque, TST. Clear?
Yes, sir.
Okay, we have seen yesterday
Yes,
that
sir.
if we introduce external resistance in the rotor circuit, then there is no change in the value of the maximum torque. But the slip at which maximum torque occurs, that will increase. So if we increase the value of external resistance, we'll get this type of speed torque characteristic, where the slip at which maximum torque occurs, your critical slip has increased, but the maximum torque is still same. If you further increase the resistance, this slip will go on increasing, and it is possible that you get the maximum torque at the time of starting. As you are increasing the rotor resistance, your starting torque is also increasing. If you go on increasing the rotor resistance, it is possible that your maximum torque occurs at the time of starting. Okay, clear? Any questions?
No, sir.
No, sir.
Represent this by RRH0. RRH0 means there is no external resistance in the rotor circuit. This characteristic. This one I'll call RRH1. This one can be RRH2. Okay. I've seen this characteristic before anywhere. This line. You see any motor that uses this line? Anyone? Have you seen any motor that uses this line?
The DC shunt motor.
We are in AC now. Induction motor, we are in asynchronous AC motors. So which characteristic will you prefer? First, second, or third? Which one? The one with RH0?
Sir, RH0, sir.
First one, sir.
First one is preferred. Why it is
First
preferred?
one,
RH1. Sir,
Why it is
RH1.
preferred? RH1? No.
Zero,
RRH0.
sir.
RRH0 is the
RH0, sir.
preferable one. Why? Why?
Low resistance, sir. Losses is less.
Yes, because as you are increasing the resistance, your copper losses will go on increasing. Correct?
So we will prefer first one because maximum torque we actually required at the starting means when we start the motor means there due to inertia means starting torque requirement is high. So there in the starting means where we will use
Maximum starting torque you are getting in the third curve, not in the first curve.
in the third yes T max where T max is written in yeah this one.
So will you use this characteristic?
Yes, because here at the starting means speed is zero. There, it is having this much of slip is equal to 1, means here at the starting maximum torque it is when you're providing.
It is giving you maximum torque, but the amount of copper losses will be very high. Your motor efficiency will be very poor.
So no problem, but starting torque requirement is so much high.
You are saying efficiency is no problem.
But because starting torque requirement is high due to inertia, motor will not start because if we will not provide this high starting torque, motor will not start.
Okay.
Means
Motor will start or not start. That depends on how much is the load torque, and whether it is greater than the starting torque or less than the starting torque. If suppose this is your load torque,
means
why do
rated
you need?
torque.
If
If
suppose
it is
this is your load torque is always less than the starting torque. Yeah, so if your load torque is greater than the starting torque, you can always increase the starting torque by inserting external resistance, but that external resistance will be removed when the motor speeds up. And then you want this curve. This is the preferred curve because it gives you the least amount of copper loss. Now you must have studied that in an induction motor, the copper loss is directly proportional to the slip, correct?
Yeah.
Yes, sir.
So for high efficiency of the motor, your induction motor speed must always be as close as possible to the synchronous speed. Okay. So my first question, does any induction motor or does any AC motor use this characteristic for working? Have you seen this characteristic before? Yes
sir
or
is
no?
wound rotor. Wound rotor means
On rotor also this type of characteristic only at the time of starting. Steady state, it will work on this characteristic, not on this one. Okay. Any other motor? Nobody in the class?
So during starting, that will follow RH2 and
No,
then
no,
we need
not at the time of
RH2.
starting. I'm saying all the time, all the time.
It's a stepper motor.
No, no.
So linear induction motor, sir. So
क्या
fan
idea
type
है ये
load.
सब? Where are you getting all these ideas? Linear, because this graph is linear, so we are saying linear induction motor. Is it so? The answer is AC servo motor. Did you study AC servo motor in your UG course?
Yes, sir. In control system.
No, sir.
Machine.
यही था ना characteristic. This was the characteristic now for AC servo motor. Yes or no? You don't remember?
Yes, sir.
AC
What,
servo
sir?
motor. How do you make an AC servo motor? What is the difference between AC servo motor and induction motor? This is the difference. The rotor resistance is high, so that you get linear operation in the entire working range from 0 up to rated speed. So okay, let us come back to the topic. Okay, so these are the speed torque characteristics of the induction motor for different values of rotor resistances. The first characteristic is without any external resistance in the rotor circuit. This is with some external resistance. If you further increase the resistance, you get this type of characteristic where the maximum torque now occurs at the time of starting. Okay, what happens if I increase the rotor resistance above RH2 also? What will happen then? In that case, you will get something like this. Okay. Yes.
Yes, sir.
So this is the characteristic with some rotor resistance R, RH3. Okay. Let us now go for braking. Let us start with regenerative braking. Now, how do you get regenerative braking in an induction motor? In the DC motor, the condition was that the back EMF should become greater than the supply voltage and the armature current should become negative. What is the condition for regenerative braking in an induction motor? When will your motor start working as a generator?
When it will run faster than its synchronous speed.
Correct. When the rotor will run at a speed greater than the synchronous speed. Who decides the synchronous speed? The supply.
So frequency and number, frequency.
Frequency and
Number of
Once the motor is constructed,
number of poles will be fixed.
fixed. Yes,
once
sir.
the motor is constructed, the number of
Yes,
poles
the
is
number-
fixed. So mainly it depends on the supply frequency. Correct. If you want to run this motor as a generator, will you keep the supply connected?
Yes, sir.
What, sir?
If you want to run this induction motor as a generator, will you keep the supply connected or you will disconnect the supply and connect the load?
Supply
Yes, sir, it
connected.
requires
Supply
supply, sir.
should
Sub-
so
Supply
supply
between
disconnected. Supply disconnected, and each means speed should be more than for regenerative braking means supply should be disconnected and load will be connected, and motor will work as a generator. Induction motor will work as a generator, and for stopping purpose means for this regenerative braking.
Sir, to energize the field winding, we always need, sir, the power, sir. So it will be connected, sir, as a generator also.
So the thing is, first of all, if you are disconnecting the supply, there is no such thing as synchronous speed then. Am I correct? If you disconnect the supply, there is no such thing as synchronous speed.
Yes, sir.
It will generate at any speed. It will generate at any speed. Provided, of course, that you are providing excitation. That excitation, if supply is not connected, that excitation is provided by capacitors, a self-excited induction generator. But if you do not have capacitors, yeah, there are three things required for generation. What are those three things?
Speed, flux,
Faraday's law of electromagnetic induction. There are three things required for generation. What are those three things? The first is a flux.
speed and relative speed between them.
Speed and relative speed.
Flux
And
and
one is
conductor
flux.
and relative speed
Yes,
between them.
yes. First is flux, second is the conductor, and the third is relative speed
Relative
between
speed
the
between
flux
them.
and the conductor. Correct. So as soon as if you are not using a self-excited induction generator, that means you do not have capacitors on the stator side. As soon as you remove the supply, your flux reduces to zero. And this is a singly excited machine. This is not a doubly excited machine. So as soon as you remove the supply, your flux becomes zero, and hence there is no chance of generation. Clear, everyone? Yes.
Yes, sir.
Yes, sir.
Yes, sir.
So an induction motor, even if you want it to work as a generator, the supply has to be connected. We'll forget that we have capacitors now. We'll forget about the concept of self-excited induction generator for now. So if your motor is connected to a supply and you want to work it as a generator, you cannot remove the supply, because as soon as you remove the supply, your magnetic flux reduces to 0, and then even if you rotate the rotor at any speed, you cannot generate power. Okay. Okay, supply has to be there. There is now two flows of power. One flow is for the active power. The active power will flow from the generator to the supply or the load. You can have a supply, you can have generator, and you can also have a load in parallel. So the active power will flow from the generator to the supply and / or load, and the reactive power will flow from the supply to the generator. Active power out of the generator, reactive power into the generator. Okay, am I clear? Was I able to explain that properly?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so if we do not have induction generators, that means right now we cannot remove the supply. Okay, so our synchronous speed is still same. If you want to, if you want regenerative braking, or you want this motor to work as a generator, that will only be possible if the speed becomes greater than the synchronous speed. Okay, only if the speed becomes greater than the synchronous speed. Okay, so regenerative braking cannot be used to stop or break the induction motor below the synchronous speed. It is only useful for braking above the synchronous speed. And this motor can run above the synchronous speed only because of an active load. And the load causes the motor to run at a speed above the synchronous speed. Then only we can use regenerative braking. Okay? Okay?
Yes, sir.
So how will be the speed torque characteristic for regenerative braking?
And in the reverse direction.
This will be the speed torque characteristic under regenerative braking for RRH0. This will be for RRH1, for RRH2, and so on. Basically, the same characteristics extended into the second quadrant above the synchronous speed. Okay, clear? Yes.
Yes, sir. Yes, sir.
Any questions? Okay. So we can only brake till this point. We cannot brake below this speed. So this braking is useful only when you have a load that can cause the motor to run at a speed above the synchronous speed. Of course, nowadays, with the advent of inverters and cycloconverters, it is possible to change the synchronous speed so that you can get regenerative braking at any speed. Okay? But at this point of our syllabus, we are not using any power electronics. So regenerative braking will be possible only when the speed is greater than the synchronous speed. Okay, can I move to the next one? Yes.
Yes, sir.
Yes, sir.
Okay, so the next braking that we're going to see is
Yes.
plugging or counter current braking. Now, how can we get plugging in the case of an induction motor? Once again, there are two cases. One case is what are the two cases? Can you hear me or not?
So by
Sir,
reversing NA to
interchange the
terminal, sir.
supply. Sir, interchange the supply terminal.
Yes, by interchanging any two supply terminals, the speed, the direction of rotation of the magnetic field can be reversed. Yes, in that case, we can get plugging. The second case is
So when the load torque is greater than the starting torque.
Yes, when the load torque is greater than the starting torque, so that your motor starts running in the opposite direction. Then also you will get plugging or counter current braking. Okay?
Yes, sir.
Suppose this is the load torque. It is greater than the starting torque. And suppose we are using this characteristic RH3. So this is your starting torque. The load torque is greater than the starting torque. So what happens? The motor, instead of moving in the forward direction, and this is the positive direction of speed, the motor, instead of moving in the forward direction, it will start moving in the negative direction. And it will run at this speed under steady state. This will be your steady state speed for this value of load torque for this motor. It will run constantly at this speed and you will get braking under this condition. Okay? Dynamic braking, sorry, plugging or counter current braking. Is this clear?
Yes, sir. Yes, sir. Yes, sir.
Under steady state, only for this value, for RRH2, you will not get steady state. Because this RRH2 curve will come like this. So this is not your stable region of operation. Okay? So you will not get constant speed there. Of course, a very large current will flow. And so you need to limit the rotor current, rotor as well as stator currents. Okay, this is one condition. The other condition is you reverse any two terminals of the supply. Now the question is, how will be the speed torque characteristics if you interchange two supply terminals? What will be the change in the speed torque characteristic? What will happen to the synchronous speed? Will it increase or decrease? I'm changing two supply terminals. What will happen to the synchronous speed? Will it increase or decrease?
So remain same, sir.
Remain same.
Correct.
Same, same, but it
Sir, in the
opposite
opposite
direction.
direction remains same.
Opposite direction.
Yes, it will remain same, but in the opposite direction. This is now your synchronous speed. Okay. What about the characteristic? Where will it go? This is your characteristic now. For some resistance and increase the rotor resistance. This is your characteristic. Okay, clear? Yes.
Yes, sir.
Okay. Suppose this was the load torque earlier. And your motor was operating at this point with RRH2. Let us say the motor was operating at this point, and suddenly you interchange two supply terminals. What will happen? Instantly your magnetic field starts rotating in the opposite direction. Okay. So the speed cannot change instantly, only the magnetic field reverses. Your motor speed or characteristic changes. So instantly your motor, the operating point shifts from here to here. Okay. And then it will start moving like this till it reaches this point. Now at this point, it is essential that you turn off the supply. Because when the speed is zero, the torque is not zero, it is negative. So you have to turn off the supply. If you don't turn off the supply, the motor starts, the operation shifts to the third quadrant. It again starts motoring, but in the opposite direction. Okay, here? Yes?
Yes, sir.
Yes, sir. Yes, sir.
Okay. This was your plugging or counter current braking. There is also a third type of braking. Before we go into that, let me tell you that plugging is the preferred braking method for induction motor. Okay? Of course, you have to see that when the speed reduces to zero, the supply is disconnected and mechanical brakes are applied to the motor. Okay, there is also a third type of braking, that is dynamic braking or rheostatic braking. Now, in case of induction motor, in case of DC motor, what we did was we kept the field winding supply constant, so that the flux remained constant, and we disconnected the armature and shunted a resistance across the armature. What do we do in case of induction motor? It has a three-phase stator winding, to which we were earlier feeding a three-phase supply, and there is no supply in the rotor. So how do you obtain dynamic braking in case of an induction motor?
Sir, here we disconnect only one supply, and then it will work as a single phase induction motor. And according to the double revolving field theory, there will be two torque. One is in the forward direction and one is in the reverse direction. So it will not able to run.
It will still run. At double revolving field theory, it will not run only at the time of starting, but now your motor is already running, and you want to brake it, correct? So if you remove one phase, it will continue to work as a single phase induction motor. It will continue to run as a single phase induction
Yes.
motor.
Yes, sir.
Yes, anyone else? Do we disconnect the complete supply and connect a rheostat across the stator? Yes or no? Hmm?
No, sir.
No. Because then the flux reduces to zero. Okay? So your motor will stop, just as it stops when you remove the supply, and you cannot control the speed of the braking. So how do you obtain dynamic braking in an induction motor?
So as you have told to us, we disconnect the supply and we connect the resistance, large resistance in the stator circuit to
When did
stop the motor
when,
immediately.
when did I say that? I did not say that. I said that I asked whether you will disconnect the supply and connect a rheostat across the stator terminals. Will
Yes,
that give us dynamic braking? I asked you. Okay, I did not tell you. Don't put things on me.
yes,
And
yes,
then I
this is the
also told you that that will not give you dynamic braking. The motor will simply stop, like it stops when you disconnect the supply. Yeah. For braking, you always need flux. You always need a flux. And as soon as you disconnect the supply, your flux disappears. Okay. So my question once again is, how do you obtain dynamic braking in an induction motor? Yes, anyone? Jairam, I need to
Sir,
call out some names now. I only hear 3 or 4 voices. Priya,
yeah,
Sumit, Subhajit, and I think Suman. Right?
sir,
Nobody else speaks. Jairam,
sir.
how to obtain dynamic braking in an induction motor?
Breaking. ठीक है।
ऋषभ राज।
Yes, sir.
क्या करें डायनेमिक ब्रेकिंग के लिए? चलो, I am